1, section 1.4, using limits to find tangents. It's also back to the tangent problem, which we talked about, I believe, in the very first day, 1.1. So this is a pretty darn important lesson here. So what we're going to do is we're going to start by drawing a function here. I don't know, just draw something like this. And let's call this function f. Okay, and what we're going to do is we're going to pick a point and we're going to call it P right here. Now, let's say I wanted to know what the instantaneous rate of change is at that point. Or another way I could say that is, let's say I wanted to know what the slope is right at this point. Remember what we talked about before? What we'd be interested in is what's the slope of the tangent line right there. So we did this before, so I'm hoping this sounds familiar. What you would do in this case is you'd pick another point. I'll put this one up here and I'll call it Q. I could pick anywhere, by the way, but I'll pick that point. Now let's figure out the coordinates of these points. It's going to be pretty hard. We don't know anything about them, right? But how about this? Let's say that this P point right here is at the x value of A. So that has an x value of A, and the Q point, let's say that it has an x value of x. Why not? That's nice and simple, right? Call it x. This point right here, the Q, would have the coordinates x, and you're probably tempted to put y here. But let's think about this. How would you get the y value? You'd plug x into f. So in other words, the y amount would be f of x. Okay, remember f of x is basically just the same as y, so hopefully that makes sense. You're taking that input, you're putting it into the f, so you get f of x, which is basically the same as y. Now, for point P, what are the coordinates there? Well, since it's at the x value of A, the x value is going to be A, and what's the y value going to be? Again, in order to get the y value, you're going to plug A this time into f, so you're going to get f of A. Okay, now we eventually want to draw the tangent line at point P. We said that's what we're interested in, is point P. But to start with, we're going to pick another point, Q, and we're going to draw a line that joins those 2 points. What do we call that line? We call the secant line. A line that goes through the function twice like that is called the secant line. So give me a second, I'm going to draw the secant line. Okay, there it is. And what I'm going to do is I'm going to try to figure out the slope of that secant line. So let's think about this. The slope of the secant line PQ, well, to get the slope of anything, when you have a line, you're going to do change in y over change in x, or rise over run if you want. So let's look at the change in y here. Well, the change in y of these 2 points is basically, let's do it in a different color. It's basically this rise, that's our change in y, and this run, that's our change in x. So how would you get this amount right here? What is that? Well, you're going f of x, but you're not going, f of x is from here all the way to the bottom. You're not going down that far, you're only going to here. So what you need to take away from it is f of a. Does that make sense? To get this height right here, this rise, you're doing f of x minus f of a. Just like, you know, in the slope formula, y1 minus y2, or y2 minus y1, whichever way you do it. So f of x minus f of a. So we can say change in y is f of x minus f of a, all divided by, all right, what about this amount? How do we get that? Well, we did f of x minus f of a for the rise, so for the run, we're doing x minus a, x1 minus x2, or x2 minus x1, whatever. So x minus a. So that's how we would get the slope of this secant line. But this secant line, the slope of this secant line, isn't actually all that close to the slope we want. We want the slope of the tangent line. Now, to get the slope of the secant line closer to the slope of the actual tangent line that we're interested in, we want to slide this point Q closer and closer and closer to point P. So I think I wrote that down here. We want to slide Q very close to P. In other words, we want X to approach A. So this is sounding like limits, doesn't it? Approaching. We want Q to approach P. And the closer Q gets to P, the secant line is going to get closer and closer and closer to the tangent line, right? And that's actually what we're interested in. We actually want to figure out the slope of the tangent line. So this brings us to something that's called the difference quotient. The difference quotient allows us to determine the derivative. Here's a word you're going to hear many times in this course. The whole course is almost about derivatives. And what a derivative is the slope of the tangent line 2f at x equals a. So in other words, if I was to draw a tangent line right here at P, why don't I do that? Okay, my yellow line's my best attempt at getting the tangent line. And as you can see, as I slide this Q closer and closer to P, if I was to redraw, this is getting kind of complicated now, but if I was to redraw the secant line between those 2 points, so this would now be the secant line, it's getting closer to the actual tangent line, isn't it? And if I move that Q even closer down, I mean, it's already pretty well exactly the tangent line. Is that making sense, or is that just too complicated? So again, what I'm saying here is that as I slide this Q closer and closer to P, and if I was to redraw the secant line, the secant line is getting closer and closer to the actual tangent line, or specifically, the slope of the secant line is getting closer and closer to the slope we're interested in, which is the slope of this yellow line, which is called the tangent line. So all that to say that the difference quotient allows us to determine the derivative, which is the slope of the tangent line, the yellow line here, of function f at point P, and that's when x equals a. So what's the difference quotient? Well, it's pretty much exactly what we just wrote up here in blue up here, except we're going to use limits when we write it. What we're going to say is that the slope is equal to the limit of change in y over change in x, wherein the change in x approaches, so let's think about this for a second. We want the change in x, remember this is our change in x, this x minus a. How big do we want that change of x to be as the Q point's getting closer and closer and closer to P? How much is the change of x approaching? It's getting smaller and smaller and smaller, right? When I move that Q down to here, for example, the change in x is only this much. If I move it even closer, it's only this much. If I move it even closer, well, now I'm going to start messing stuff up. If I move it even closer, the change of x is very, very little whatsoever. So we want our change of x to approach 0. Alright, so what's that equal to is the limit of, what did we say change in y over change of x was equal to? This right here, f of x minus f of a all divided by x minus a. Now, we're going to have a different approaching here. We're going to have as x approaches, so what do we want x to approach? We want the x, if you just think about this x here, we want this x to move further and further this way. What is x approaching? Like literally, what is it getting closer and closer to as I do this? X is approaching a, because we want the change in x, this amount right here, to be as small as possible. So we want our x to approach a. So that's what we're going to put, x approaching a. This is the derivative. It's also called the difference quotient, and this is absolutely critical. It's probably the most important formula that I'm going to give you in this whole course. Although we're going to stop using it in about a 1 month time, and you're going to learn to hate this thing. But for now, love it. So here we go. We're going to find the slope and the equation of the tangent line to the curve y equals 2x squared plus 4x minus 1 at the point 2, 15. Okay, you need to be clear about two things. One, what's f of x? And two, what's a? So f of x is no problem. F of x is just the same as y, right? So f of x is 2x squared plus 4x minus 1. Now, your a value, remember, that was the x value of the point you're actually interested in. The point we're interested here is 215, so our a value would be 2. Okay, with that figured out, we can start to use this formula right here. We're going to say the limit as x approaches a, well that's 2, of f of x minus f of, oh, there's that a again. What am I going to write there? 2. All over x minus, there's a again, 2. Okay, well let's do that. Let's do exactly what's asking. So we're going to have the limit as x approaches 2 of f of x. Well, what's f of x? We just said what f of x is. F of x is this. So 2x squared plus 4x minus 1, I'm going to put that in brackets, minus, now f of 2. How do I do that? I plug 2 into all these x's here. So I get 2 times 2 squared. Well, that's 2 squared is 4 times 2 is 8, plus 4 times 2 is another 8, and then minus 1, all over x minus 2. Let's keep going. This is a lot of steps to these questions. So let's combine terms and stuff. So we have 2x squared plus 4x minus 1 minus 8 plus 8 is 16 minus 1 is 15 all over x minus 2. You could probably skip some steps. It's a bit of overkill here. So now what I have, 2x squared plus 4x, and I have minus 1 and minus 15. That's minus 16 over x minus 2. Okay, what do you think we should do now? Now we should factor the top. So still limit, take out a 2, and I'm left with x squared plus 2x minus 8 over x minus 2. Keep going. The limit as x approaches 2 of 2. You can factor this. Simple trinomial. Two numbers that multiply to 8 and subtract to 2 are 4 and 2. So we'd have x plus 4 and x minus 2 all over x minus 2. Hey, this worked out very nicely because these cancel each other out. So now we can actually evaluate the limit. Now, what's the first thing we always try to do when we evaluate limits? We try to plug this value in and see if we get 0 on the bottom. And you don't. So we can do that. We can just substitute. So we get 2 and then 2 plus 4. Well, that's 2 times 6, which equals 12. Our slope is 12. Whew, that was a lot of work. Guess what? We're not done. It doesn't ask just for the slope. It asks for the slope and the equation. But we're almost done because we can do this very quickly. We have the slope and we have the point right up here. So to get the equation, we just need to use point slope form. So we have y minus y1 equals m times x minus x1. So it's y minus y1 is 15 equals m. Well, that's what we just found down here. Our slope is 12. So 12, and then x minus x1 is 2. Away we go. Y equals, I'm going to expand 12x minus 24. I'm also going to move the negative 15 over, so it becomes plus 15. So I get y equals 12x minus 9. And because we like to put it in general form in this textbook we're using, I'm going to move the y over to this side, so I get 12x minus y minus 9 equals 0, or I'll put it on this side, equals 0, and we've got our answer. Okay, believe it or not, what we're now going to do is practically the same thing over again, but way faster. There's actually an alternate difference quotient, like another difference quotient. So again, here's my function f. We're going to pick a point P. We're interested in the tangent, the slope of the tangent line that goes to that point, but we're going to pick another point Q to help us out. So we're going to call this point, give it the coordinates A again, so our x value here is A at this point, which means the y value of this would be f of A, just like before. Now here's where we're going to do something a little bit different. We're not going to call this point here, we're not going to call this x value right here, we're not going to call it x, we're actually going to call it A plus H. Okay, so then this Q point has values of A plus H is its x value, and its y value would be f of A plus H. If you wanted to go with the y value, you would plug A plus H into f. Okay, and I'm going to draw the secant line again. Okay, so the blue line is the secant line, and what we're interested in is finding the slope of that secant line, the slope of PQ. And let's go straight to the limit here. So remember, it equals change in y over change of x. Okay, change in y, so that's this amount, right? Change in y is right here. How much is that? Well, it's this y amount, f of A plus H, take away this y amount, f of A. So we want to figure out f of A plus H minus f of A. That's the change in y. How about our change of x? Here's our change of x. That is this x value, A plus H, minus this x value, which is A. So I'll write that down, A plus H minus A. And what do we actually want here? We want A plus H to approach A, right? We want this point, right? As Q gets closer and closer to P here, this A plus H is going to get closer and closer to A. So what we want is for A plus H to approach A. Okay, I'm sure some of you are observant here and notice something on the bottom. A plus h minus a, you can cancel the a's here, subtract the a's, like terms, you just end up with h. So actually what we could say is that the limit of f of a plus h minus f of a all over h, because that's the only thing that's left. So now if I go back and I simplify this, we said that our change in x amount is actually just equal to h. So if this is h, what do we want h to approach? How much do we want h to eventually equal? As this gets smaller and smaller, as this q is moving closer and closer to p here, this h is getting smaller and smaller and smaller. How small do we want h to get? Like how much do we want to approach? We want h to approach 0. So in words, what we need to do is we need to slide q very, very close to p. In other words, we want h to approach 0, which gives us our alternate difference quotient, which is basically exactly, well, it is exactly what I've written up here. So I know this is a little bit redundant, but we're going to write it again down here. We're interested in the slope. The slope is equal to the change in y divided by the change of x, and what we want to happen is we want the change of x to approach 0. We don't want there to be a change of x. We want this q to be as close as p to p as possible. And what we've just seen above by doing a few things is we found that this is equal to the limit of f of a plus h minus f of a all divided by h as h approaches 0. This is an h. Okay, so let's use the second formula to find the slope of the tangent line to the curve y equals the square root of x minus 2 at the point 6, 2. So again, we better figure out what f of x is, and we better figure out what a is. So f of x is no problem, same as y, so we have the square root of x minus 2. A, remember that's the x value and the point you're interested in. So in this case, it's 6. Okay, so now what we're interested in is the limit of f of a plus h, but we said that a is 6, so 6 plus h minus f of a, but a is 6, all divided by h when h approaches 0. So let's go ahead and do that. The limit as h approaches 0 of f of 6 plus h. So how are we going to figure that out? F of 6 plus h. You're going to plug 6 plus h into this right here, wherever the x is. So that x right there. So we're going to have square root of 6 plus h minus 2 minus f of 6. What's that mean? That means plug 6 into that x. So square root of 6 minus 2 all divided by h. And as you can see, we have a lot more simplifying to go here. So the limit as h approaches 0, well here we have 6 minus 2, so we have 4 plus h. And here we have 6 minus 2 is 4, and the square root of 4 is 2. So we get the square root of 4 plus h minus 2 all over h. And you might say to yourself, I guess I'll now substitute 0 in. But you can't, because you get 0 on the bottom. So do you remember the trick that you often use when you're stuck in this situation with limits and you have a square root? You're going to multiply top and bottom by the conjugate. You're going to rationalize the numerator. So you're going to multiply by the square root, this is a bracket, the square root of 4 plus h plus 2. And what you do the top, you got to do the bottom. So multiply by 4 plus h plus 2, the square root of 4 plus h plus 2. Okay, here we go. We're going to multiply square root of 4 plus h times the square root of 4 plus h, which equals 4 plus h. Then the next two terms are going to cancel, and then you're going to go negative 2 times positive 2, which is negative 4. And of course, we still have our limit as h approaches 0. On the bottom, just leave it. So we have h, and then we have this bit, square root of 4 plus h plus 2. Okay, now we can cancel out the 4 and the negative 4. You can also cancel out the h on top and the h on the bottom. So what's left on top is a 1, and now you are able to start substituting. So we have 1 on top, we have the square root of 4 plus 0 on the bottom, and then we have plus 2. So that's 1 over, this is 4 plus 0 is 4, square root of 4 is 2 plus 2, so 1 over 4 is our answer. That took a lot of time, didn't it? And that is the slope of the tangent line to this curve at that point. Oh gosh, why do I do this? It says use both formulas to find the slope of the tangent line to the function xy equals 1 at the point -2, -1/2. My goodness. Okay, well, let's see how far we get here. The first thing, you want to isolate the y, and that's easy to do. So you'd have y equals 1 over x. So we need to know what f of x is, and more or less did that just now. Y equals 1 over x. And we need to figure out what a is. What's the point we're interested in? Right here. And the x value is -2, so that's my a value. So for the first formula, remember, it was the limit of f of x minus f of a divided by x minus a as x approaches a. So let's see if we can do this fairly quickly. The limit x approaches a, well, a is -2, so as x approaches -2, then we have to do f of x. Well, f of x is just 1 over x minus f of a. Remember, a is -2, so f of -2. So we got to put -2 in right here. So you get 1 over -2 divided by x minus a. So that's x minus -2. Okay, the limit as x approaches -2 of 1 over x plus 1 over 2. Right? Take away a negative here, so it's going to be plus, and same on the bottom, it's going to be x plus 2. Something you often do when you have compound fractions, remember, is you're going to get common denominators. So I would suggest that's what we should do next. I'm going to keep this the same. So let's get our common denominators in the top here. Common denominator would be 2x, right? So we're going to have 2x. What do you have to multiply the x by to get 2x? 2. Do the same at the top, you get 2. What do you have to multiply 2 by to get 2x? X. Do the same at the top, you get x. Now, we're going to divide by x plus 2. But dividing by something is the same as multiplying by the reciprocal. So I'm going to multiply by 1 over x plus 2. Why is this good news? Because we have 2 plus x and x plus 2. Order doesn't matter when you're adding. So this and this can be canceled out. Now we're able to substitute. What you're left with is 1 over 2 times, plug your -2 in, you end up with 1 over -4 or -1/4. So that's the first way you could do it. The second way you could do it is you could use the new formula that we just found out, the alternate formula. So that one says that the limit of f of a plus h minus f of a all divided by h as h approaches 0. So here we go. The limit as h approaches 0 of f of a plus h. So first of all, remember that a is -2. So we got to put -2 plus h into this x. So that's 1 over -2 plus h minus f of a. A is -2, so we got to put -2 into here, and we get 1 over -2, all divided by h. Okay, so let's simplify this a little bit. So we still have the limit h approaches 0, so my writing's getting so bad here. So we could turn this around. Rather than having -2 plus h, we could have h minus 2. Take away negatives, so that's plus 1 over 2 all over h. So again, let's find a common denominator here. Compound fractions, good thing to do. So our common denominator is h minus 2 times 2. So what do we have to multiply this by? By 2. So again, our common denominator is going to be 2 and then h minus 2. So we have to multiply this by 2, same with the top. We have to multiply this by h minus 2, same with the top. And that's all divided by h, but dividing by h is the same as multiplying by the reciprocal, which is 1 over h. Okay, let's see what cancels out here. 2 take away 2 cancels. We have an h on top and an h on the bottom, so that cancels. So all we're left with is a 1 on the top, and then 2, we can substitute in now. 0 take away 2, that's -2. 1 times 2, 1 over -4 or -1 over 4. We got exactly the same answer. Is there one of those two methods you like more? I probably prefer the first one a little bit. I think the other one actually turns out being a little bit more commonly used. But they're both important. There you go, another epically long video. I'm so sorry, everyone.